Everybody, so we're not meeting in person for a help session, but I do have this a summary of what to expect for your upcoming exam because we have covered everything that you'll see on your exam, and if you're preparing for your exam over the break, then I want to give you a little heads up. So please do prepare if you have time, because there are other things that you're going to have to do when you come back. So please plan accordingly as far as your other classes, organic and what have you. So we're picking up middle of chapter 2 and moving up to about 3/4 of the way through chapter 4. um, so in chapter 2, you're picking up in the section on capacitance. So you need to understand, what is a capacitor and what is it used for? It's used to store energy. Also understand how to determine the charge on that capacitor, that Q is equal to CV, and then how to calculate the capacitance based on its dimensions. Ugh, sorry. Epsilon naught. How to calculate the capacitance based on its dimensions. There are a variety of questions that I asked in that chapter. Make sure you're practicing those and know how to answer them. And then in the end of chapter 2, you're going to see capacitors in series. You'll probably have, I don't know, a single question on how to calculate the voltage and charge on capacitors in series. Also, you'll see capacitors in parallel. And then finally, you'll see capacitors in combination circuits. This is the simplest combination circuit. Of course, you'll probably see more complicated ones. You will likely have a capacitor problem as one of your free response questions. I'll show you an example of that here in just a second. Okay, so make sure you know how to do capacitors in it's series and parallel and combination. And we spent a lot of time on those circuits, so go back and review those. You'll see both quantitative and qualitative questions. So questions that are related to the numbers, just calculating what is the charge, what is the voltage on each of these capacitors, and then also, what happens when you take a capacitor out, or what happens if one of the capacitors increases, or something along those lines. You can see examples of those questions in the past exams and in the notes. Um, Also, there was a very brief thing about calculating the energy on capacitors. Let me just say, though, if you go further into chapter 4, you see RC circuits. So if you ever encounter one of these will not be on the exam, but they might sometimes be on exam too. An RC circuit occurs when you have a resistor and a capacitor. It will have this e to the minus t over RC, or it might talk about a time constant tau. So if you encounter a problem like that, that will not be on the next exam. We just simply won't have time. So I'm going to push that back to exam 3. So the end of chapter 4, which includes household circuits and RC circuits, will be on the exam 3. That happens often. It doesn't happen always, but you'll see that in some of the exams. Okay, now moving on into chapter 3. So chapter 3 was a short chapter. The first thing we need to know is just know how to define current. That's Q over T. I'll probably have a simple question just asking you, if you have a certain current, how much charge passes that point in a given amount of time. You just need to know that definition for current. Also know that in our uh, in our convention, we're assuming that current flows in this direction. And remember, this is the direction that protons would flow. We base that on the work that Benjamin Franklin did on that was pioneering. I also need you to know how to use an ammeter and a voltmeter. So when I'm using an ammeter, I hook it up in parallel with the resistor that I want to know, and an ammeter has a small resistance. It has a small resistance because, well, I don't want to see a big potential difference across an ammeter. That would just change the circuit. So I have something that has a very small resistance, so effectively it's not even there. It's basically like just adding a wire. And if I'm measuring a voltage, I hook up my voltmeter in parallel. So my voltmeter gets hooked up like that, and a voltmeter has a very big resistance. The reason it has a big resistance is because that gives it a very small change in potential. Oh no, let's not think about it that way. Never mind. No, don't think about it that way. What it happens is that I get a very small current that goes across that voltmeter. Anyway, not terribly important. Just forget that I said that. Okay. Also, we need to know Ohm's law, V equals IR, and know how to apply Ohm's law and how to use Ohm's law. Know the difference between ohmic and non-ohmic. And then finally, in chapter 3, we talked about the geometric properties of resistors. R is equal to rho L over A. So if I have a resistor, it just consists of a certain material, it has a length, it has a cross-sectional area. If my area goes up, that means my resistance goes down. So if that resistor just gets bigger and bigger, like the area expands in this direction, then I'm adding more conduction electrons, and it makes it easier for electricity to flow, so the resistance will go down. If I make the length go up, then that means the resistance will go up. So it's like trying to siphon gas through a really long hose. We did do a thing where we have an unknown metal where you had to calculate what rho was, and then once you find rho, you take a table of data, and you can determine that unknown metal. It's a nice, easy way to calculate or determine what is an unknown metal. And then finally, we talked about power. Power in that chapter is equal to V times I. We had some other equations that were just derived by substituting Ohm's law in for either V or I. And these equations are, of course, on your equation sheet, but it is useful just to be familiar with them. Now, finally, in chapter 4, we have our DC circuits. And in that, you're going to first see the idea of internal resistance. Remember, we use the lowercase r for this. And the internal resistance is if I have a battery, that battery is not perfect. It has some amount of resistance. So if I imagine my battery, this is like your car battery. If I imagine the schematic of it, it would be a source of EMF, or electromotive force, and an internal resistance. So that's E and that's R. Otherwise, we treat it, so if we imagine it in that way, then we treat it just like we would any other resistor. And so we saw that, and we can apply things like the loop rule. Then we'll also see resistors in series. Okay, we'll see resistors in parallel, and we'll see resistors in combination. So maybe something like this. That's a combination circuit. That's not the simplest you could have. The simplest you could have would look like that. So you need to know how to do all of those. We spent considerable time on doing those. I'll probably focus more on the combination circuits, but I do expect that you'll have questions about both just a simple series circuit and a simple parallel circuit. We'll see on the multiple choice. But of course, for the combination circuits, you have to know how to do the series and parallel circuits. I expect that you will have a free response that will be a slightly complicated, 6 to 8 resistors combination circuit. All right, and then finally, we've just started this, and so we'll spend more time on it. That is how to apply these rules for multi-loop circuits. I remember we had two rules on Kirchhoff's rules. And Kirchhoff's rules included the loop rule. Loop rule, that is the sum of the voltages across a loop is equal to 0, and the junction rule. We just presented this today in class, and the junction rule just says that IN is equal to I out. We also had some, what would you call it, just procedures for how to apply these rules on what is the sign of these potentials. Do I have a positive change in potential, or do I have a negative change in potential? You need to make sure that you know how to apply those rules for multi-loop circuits. We did do a single loop circuit in class, but then we also did a multi-loop circuit. So your multi-loop circuit you'll have on your free response. Be careful. Sometimes I draw multi-loop circuits like this, and sometimes I draw them like this. They're really the same, where you apply the rules, the loop rule for the top loop, the loop rule for the bottom loop, and then the loop rule for the big loop, or the left, the right, or the big loop. So make sure that you understand and know how to apply those different directions and how we apply those rules for our multi-loop circuits. So looking at our free response, your free response is probably going to be, well, a lot like this. So here, notice I have a slightly complicated capacitor circuit. The difficult part about this capacitor circuit, and you should look back at previous exams, is really just redrawing the circuit so that you see it in the right format. And if you can do that, then you're probably going to get it just right. So for example, let's do this one. I always start off the positive side of my battery just to be consistent so that you're always doing the same thing. You could go from the other side of the battery and that would be just fine, but just to be consistent, I'll always start off the positive side of my battery and start redrawing that circuit. Now, when I come to this point, notice it looks like it splits into two wires, but really I have one wire there, and then I have a third wire here. So I actually get a split in this junction into three different wires. Um, and those I get C1 right here. I get what's that called? C2 right here. And then I get C3 and C4 because notice here if I go here, those are not separated by a junction. This, not a junction, right? That's just a bend in the wire. So I can redraw that parallel branch and then notice after it goes through these, they all come back to the same point. So I redraw that, cut it off. Let me put in these values. I have 3, 2, and then 2 and 2. Those are all the capacitances. And then I have another one that is 3 microfarads, and then I go back to my battery, and my battery was what, 12 volts. Okay, now that I've done that, I've done most of the problem. And that's probably the hardest part of the problem for most of you. So practice that, look back at the past exams and look for these types of diagrams and just practice redrawing them. Looking for the junctions, looking for the capacitors that are in series with one another, and looking for those branches that are in parallel with one another. Now that I've done this, I'm going to determine our redraw it so that I have it in a simplified format. So here 2 and 2, that's going to be 4. Let's see. I think I might have changed this. Hold on just a second. Let me look into this. Okay, sorry, I actually see my mistake. Y'all should have stopped me. So here where I have 4, this should really be 1 over 1 over 2 plus 1 over 2, and that's equal to 1. And that illustrates a point here that you have to be careful when you're doing these, because the reason I did that is because I'm thinking about resistors. And remember the rules for equivalent resistance are flip-flopped from the rules for equivalent capacitance. That equivalent capacitance for capacitors in series is that 1 over C plus 1 over C. So just be careful. Don't make the same mistake as I did. Don't be like me. Okay? Do not be like me. Um, so that's 3, 2, and 1, and then 3. But now 3 plus 2 plus 1, that's equal to 6. And this is equal to 3. I have 12 volts right here. Now you can probably begin to step back and think about what are the voltages. I know that this is going to have 4 volts. This is going to have 8 volts. Remember, because big capacitors have small voltages. And 6 is twice 3, so the voltage is going to be half the other voltage, and it has to add up to equal to 12. So if I get that, I'm almost done. That gives me 4 volts there. That gives me 4 volts there. These two capacitors would have 4 volts together, but they're going to split that up into 2 volts and 2 volts. So now I have the voltages across all of these capacitors, and I can go back and find any charges or voltages that I ask. You really, on any of these problems, you're going to have to find them all. And then also the equivalent capacitance, of course, is going to be 2 microfarads because I have this 6 and 3, 1 over 1 over 6 plus 1 over 3. Okay, so you'll have a question like that, and then you're also going to have a question like this, where you have a number of resistors. I'm not going to draw it out all funky on a grid like the previous question. It'll be sort of more standard format, but it'll look something like this. Let's just work through this. So I have 12, the 2 and 2 in parallel. That gives me 1 ohm. Here, this is going to be 6 ohms, 2 plus 4, and then 6 and 3 in parallel are 2 ohms. So then that gives me a 3 ohm resistor with, what is it, 12 volts. That means I have a current equal to 4 amps. So 4 amps here, 4 amps here. That means I have 4 volts here and 8 volts here. So I have 4 volts, 4 volts, 8 volts. And then up here, I have 8 volts across these two resistors. And then that means that I'm going to have a current equal to 8 volts divided by 6 ohms, or 4/3 amps. So I have 4/3 amps on each of those. That means that the resistors will have, well, R3, or rather V3 across R3 will be equal to I times R3, or 4/3 times 2 ohms. That's 8/3 volts. And then V4 is going to be what? 16/3. Did I do that right? Let's see. 4 times, yeah, 16/3 volts. And then the combined voltage across these two resistors will be 8/3 plus 16/3, which is 24/3 volts, which is equal to 8 volts, which is what you had across both resistors, but since they're in series, they split it up. Okay, so you're going to have a question like that. And then finally, you're going to have a question like this. We've done one or two of these already, and if you really want to practice something, well, I don't know, if you want to practice this, really practice it all, frankly. I mean, if you have time, spend time practicing this over the holiday. Um, I want to know, it's going to be a question very much like this. Of course, the numbers and the layout will be different. I might remember, don't be thrown off if I give it to you like that. If I give it to you in a portrait, you do it the exact same way. But um, I'll give it to you in this way. Now, if you're practicing in the homework, so in the back of your chapter, you have some homework questions, be aware that those questions are a little more difficult mathematically. I think they're probably still useful for you to practice because you'll see more of the details about how to work it out. But on the exam, I'm going to give you an easier problem mathematically that you can work out the same way, but mathematically it's going to be a little easier. And the way that it'll be mathematically easier is probably because probably likely on one of these branches, you're not going to have a resistor, and that makes it quite a bit easier. All right, so first thing we do is we identify where our three currents are. I have three currents there, and there. I've already labeled them as I1, 2, and 3, but you need to label the directions for those currents. I'm just going to label them in some random way. It doesn't really matter how I label those currents, but I've labeled them now I1, 2, and 3. And I want to write out the equations for those. Now, if I'm clever, I can just write a couple of equations that will be pretty easy to solve. And the equations that I'm going to write are for the bottom loop and the big loop. Let's just write them first, and then I'll tell you why those are superior to writing an equation for the top loop. The bottom loop, let's start here and go in that direction. So that's going to be positive 2 volts plus 6I2 plus 8 volts is equal to 0. Look, I can go ahead and solve this. That's 10, so I2 is equal to 5/3 amps. Did I do that right? No, negative 5/3 amps. Oops, that means that I I wrote the direction for I2 incorrectly. So that's the bottom loop, and I've already solved now for I2, so I'm almost done. I'm just going to go ahead and do I2 is equal to 5/3 amps, and I chose it incorrectly. That means instead of going to the right, it should go to the left. Now let's do the, what did I say, the big loop. I'm going to do the big loop, and then I'll tell you why I didn't do the top loop. So the big loop, I'll go in the same direction. Start here and go that direction. So that's positive 2, positive 4, because I'm coming up here and going through here, and then plus 2I1. That's equal to 0. So I get I1 is equal to negative 6. So that's negative 3 amps. So this I1 is 3 amps. And I said that I1 was to the left, so it's really to the right. Okay, so now I want to figure out what is, or let me go ahead and write the equation for the top loop, but we're not going to use it. I'm going to start here and go in that direction. So for the top loop, it's going to be 4 plus 2I1 minus 8 minus 6I2. That's equal to 0. Look, the reason I didn't use the top loop is because, look, it has two unknowns in it. And I can get those two unknowns from these equations. So look for the loop that has two resistors in it, because you will have a loop in your circuit that has two resistors, but you'll have two loops that only have one resistor. And so I can choose those two loops, and it'll make my math a lot easier. As I said, in the chapter, the back of the chapter homework problems, I have a problem there that has resistors in every loop and sometimes more than one. And see, you can look and see how we solve that system of equations. You've done that before. It's not impossible. It's really not that hard. You're capable of it, but you're not going to have to do that on the test to solve that system of three equations with three unknowns. It gets a little hairy, and it's just, I know that you can do it, but I don't know. It's difficult to do on an exam. But I'm still missing I3. So I need to figure out what I3 is. Remember, we don't have I3 in any of these equations because we don't have I3 in that bottom loop. Or excuse me, we don't have a resistor in that bottom loop. So I3 never shows up in any of the loop equations, but it will show up in the junction rule. So I can write the junction rule. I'm just going to pick a junction. I have I2, or excuse me, I3 coming in, and I1 and I2 going out. Which one am I looking for? I'm looking for I3. Oh, so this is easy. I1 is -3. Be careful. I keep that negative until the very, very end when I write my answer. -3 minus 5/3. So that's, what's that? 9/3 minus 14/3. So I2 then is 14/3 amps. I now drop the negative, and I3, I had chosen it in this direction, so that means that it's actually, I chose it to the left, that means it's actually to the right. Okay? By the way, I can put in any of those values into any of these equations, and they should come out consistently. If they don't, then I made a mistake somewhere. So if you have extra time on your test, please do that. Okay, let's see, how long have I been going here? We have some more time. Let's just look at some of these old tests. These are great examples of test problems. You know what? Hold on. Give me just a second. So I'm realizing that we didn't have capacitors on our exam one. Whereas, for example, on this spring 21 exam, we had capacitors on our exam one. So you'll need to go back and pick up those questions on exam one that you didn't study for exam one, the ones all about capacitors, the dimensions of the capacitor, Q equals CV, all that jazz, and make sure that you get that. So don't forget that. Make sure you're picking up those capacitors from chapter 2. All of capacitors from chapter 2 will be on your exam 2. Okay? Um, so make sure you know how to do these. Let's just do one of these combination circuits here. What is the charge on C1? So the first thing I want to do is find the equivalent capacitance. I have C1 right there. I have two capacitors in parallel here and here. Those combine to give me 2 microfarads. This is 2 microfarads divided by, and I have 12 volts across them. Because these are identical capacitors, I know that they each get 6 volts, also because they're in series. Notice they are in series. There's no junction. That's just a bend in the wire, not a junction. So I have 6 volts and 6 volts on each of those. So I have 6 volts here. By the way, I have 6 volts here and here because those are in parallel. Capacitors in parallel share the same voltage. Capacitors in series split up the voltage or divide the voltage. So I'm looking for the charge on C1. Anytime I get two quantities, I can figure out the third quantity. Q is equal to CV, so that's 2 times 6, and that's equal to 12. Make sure that you're just aware of the rules that we have, that you're working on that. Here's a application of that. Q is equal to I times T. So here I'm looking, oh, what am I doing here? I'm looking for the voltage here, actually. V is equal to I times R. So I is equal to Q divided by T times R. And so then I can figure out what is the voltage. That would be 1200 coulombs divided by the time, which is 4 minutes, times 60 seconds, times R, which is 10 ohms. So that gives me my current times my resistance. What's that? 4 times 60. What's that? 240. I think it's 5 times 10. I think that's right. 50 volts. I'm pretty sure that's the right answer. Okay. Make sure that you are looking at these questions. Students often have difficulty with these types of questions, and indeed, in class, people have difficulty with these as well. So here, if I want to know which produces the most power, that is, which one has the highest voltage. Doesn't really matter what my voltage is here, 12 or whatever. I could also think about, excuse me, I could also think about which has the bigger current. Which current is biggest? The one that has the bigger voltage will have the bigger current. So you can think about how the current splits up. Here, my total current, this is my biggest current. That current will split into two pieces, I divided by 2, I divided by 2, and then they'll come back together and give me I here. And then over here, I'm going to get less current over here than I get over here. Let's see, what would this be? This would be I divided by 3, and this would be 2I divided by 3, because they have to add up to equal to I. So I'd get more current through R5, and then that means I'll have the most power through that. This is really just asking which resistor gets the most current. We've done that question. In fact, we did that exact question in one of the concept tests. Make sure you know how to do this. This is really just a R equals rho L over A, and then solving for rho. And then once you find rho, you can pick out which is the appropriate. Okay. You will have a question like this where you have a multi-loop circuit, and I ask you to pick out the right equation. We have not done an exact question like this yet, but we will when we return on Friday. But um, so here, if I wanted to pick out the right equations, the way you do this is, well, first is just the junction rule. Which one is the junction rule? You just pick a junction. Here I have I1 and I2 and I3 all coming in. So the junction rule should say I1 plus I2 plus I3 equals to 0, but that's obviously not what it says, so that's not right. Now I look at, I have this 4 right here, that's referring to this, and I should be going in this direction because it's positive, so I have plus 4 minus 2I1. So far that's correct because I'm going with the current, so it should be negative. Minus 8, that's correct, plus 6I2. So B is correct, that equation is correct, and then I come back up to here. Um, let's look at the next one. 4I2, where's 4I2? Look, I2 is only right here, so that, excuse me, no, 4I1. 4I1. I don't have a 4 ohm resistor in this top branch, so that's not right. You might have thought that this was the 4, but that's not correct. That you don't consider the current when you're determining the voltage difference across a battery. And then finally, 8 plus 2, that would be going right here. 8 plus 2 minus 6I2. Okay, this is correct too. So B and D both are correct. Whew, okay. I think that's going to be the end for me. Even though it's a short help session, it's a little faster paced. So let me know if you have any questions. Again, our exam is not on Monday. It's going to be on the following Wednesday. So what's today's Friday? 1 week from this coming Wednesday. So we come back on Friday, then we'll have class again on Monday, and then we'll have our exam on Wednesday. That is different from what is in the syllabus, and I'll send you all a notice about that. And it will cover the last part of chapter 2, all of chapter 3, and the first part of chapter 4. You will not have home circuits. Let's see if there's any home circuits here. No, I didn't have any here. Let's see. I think more recent exams have not been getting to home circuits. Yeah, I don't see any home circuits. Really, if you see anything about, your household, circuit breakers, GFCIs, those sorts of things. Yeah, I don't see any here about home circuits. So it looks like if you're just picking up those last questions on capacitors, oh, here we go. So these are about home circuits. This one, this one, this one. You will not see questions like that. Okay, and you will not see any RC circuits, but you don't usually see those in exam 2. So focus on exam 2. Also pick up those capacitor questions that we missed in exam 1 from previous semesters. That's all. I hope y'all have a great holiday, and I will see you all on Friday. I know you may be inclined to think that we don't have class on Friday, but we do indeed have class on Friday, so it'll be an important day for you to get there, as I have one more thing that I want to show you about the junction rule. So you might pick up some of that as you're practicing, but I'll definitely show you on Friday. Have a great holiday. See you next week.